Within the section 15.6, we talk also about parametric surfaces, where you can compute the surface integral, where the surface may be defined using certain parameters. Here, for a surface S given by a vector value function R of uv, this is just generic for whatever application that you as a scientist, a mathematician, or an engineer may be working on, that there may be given to you, or you may, with the data that you have collected, notice that certain parameters hold true for whatever you are trying to observe. So this R of uv is generic, some generic function where x depends on u and v, y and z also depends on u and v. What are u and v? Those are the parameters. They could be time, could be some type of energy, such as heat, temperature, that is. It could vary from place to place. So here, mathematically, we just speak generically about a parametric surface. So we say that this parametric surface is defined on some region D in the UV plane. And here we can show that the surface integral of F over S, the same formula that we had before, what we're looking for, is given now by this parametric surface of the double integral over this new region. F of X depends on U and V, or Y depends on U and V, Z depends on U and V. Do you see this norm here? That is to represent here for us the norm of the gradient of G. But here I'm not dealing with G. We're dealing with this new function, vector value function R. But it represents that. What is this guy right here? This is a normal vector. This cross product, the norm of that is just the length, but the cross product, you recall, of two vectors is said to be orthogonal to each vector. So this cross product is said to be the perpendicular sticking up outward vector n coming from the vectors u sub r sub u and then r sub v. I put down here below the formula to calculating this cross product. So we get to that with the problem. And here the author gives very similarities between here little ds and then capital DS. And so little ds with the line integral and then capital DS with the surface integral. So this cross product is the determinant. Here the first row is I, J, and K. The second row, partial derivatives of U based on X, Y, and Z that's given in the problem. And then the third row would be the partials of X, Y, and Z with respect to V. Now, let's see if we can illustrate that and show you that with this particular problem. So what I want you to see is that when you convert f of x, y with respect to this vector value function r, this guy becomes x. Here, this is x, right? And then this is y without the j. So x plus y becomes 2 cosine u plus 2 sine u. That's f. Now ds is this cross product of the norm of r sub u cross with r sub v, then times dA. What is this area that A is representing, this dA is representing? Well, here, this region, it goes from 0 to power over 2 for u, and then from 0 to 1 for v. So this formula is this. This is the double integral over the surface of f of x, y, ds. This becomes the double integral over d. What's d? D is defined there, of f of r with respect to u and v. So this is the x with respect to u and v, comma, here the y with respect to u and v. And that's all we have. We don't have z here for this particular problem. And then this is times that norm of the cross product. And times dA. Let's see if we can put everything that we need in there now. Oh, we got to find that that norm. That's like the big part. Everything else straightforward. So this is, I tell you what, better go ahead and get that now, and we just plug everything into the formula. So this, the first thing we need is the cross product. So this is I, J, K, and then this is the partial of x with respect to u, the partial of y with respect to u, and the partial of z with respect to u. And then here, this is the partial of x with respect to v, the partial of y with respect to v, the partial of z with respect to v. So this is I, J, K. So we look at R, that's what we're going by. Here R is 2 cosine u I plus 2 sine uj plus vk. So we're going to take first the partial of R with respect to u. And that's what this second row is. So this is negative 2 sine u, and then we take the partial of the y with respect to u. This is 2 cosine u. Take the partial of z with respect to u, 0. Then we take the partial of x with respect to v. Well, there's no x there. There's no v there, so this is 0. The partial of the y with respect to v, there's no v there. This is 0. The partial of this term with respect to v, well, it's 1. We just do the cofactor expansion. I'm going to do the cofactor expansion along here, this position. You say why? Because I have 2 zeros there. It's going to help me in the cancellation. So what you have left is just the cross product here. So anytime you have a row with 2 zeros, you got one term there, you can do that cofactor expansion. Makes it a little bit easier to compute the determinant, and that's all you're doing. When you have these slash lines, that means the determinant. So this is 2 cosine ui. Then it's minus, right, negative 2 sine uj. So minus this minus becomes a plus 2 sine uj. Now you can do that cofactor expansion that long way that we showed you before, and that's fine too. you get the same thing, right? So delete the ith row and column, so we get 2 cosine u. Come to j, delete the jth row and column, so that gives us negative 2 sine u. Then you come to k, delete the kth row and column, right here and there, so that gives us 0 minus 0 is 0. So you get the same thing, 2 cosine ui plus 2 sine uj. So now we need its norm. So this is the square root of the 2 cosine u to be squared plus 2 sine u to be squared. Well, that gives us 4 times cosine squared u plus sine squared u. Well, that's equal to, well, the square root of 4 is 2, and then cosine squared u plus sine squared u is 1, and so this is just 2. So the problem at hand is the double integral. Here we have the function with respect to u and v. So this is the function x plus y, which is 2 cosine u plus 2 sine u. Let's put that there. This is times that norm of the cross product, which is 2. Then here we have du dv. You can do dv du, but u goes from 0 to the power of 2, and v goes from 0 to 1. 0 power of 2, and then 0 to 1. We factor out the 2, so it's 2 times 2 is 4 times the integral from 0 to 1, the integral from 0 to the power of 2. And here we have cosine u plus sine u du dv. Integrate with respect to u. And so this is 4 times the integral from 0 to 1. We get sine u minus cosine u. That's evaluated from 0 to power of 2. And then this is dv there. This is 4 times the integral from 0 to 1. Evaluate the sine at power of 2, we get 1. Minus cosine of power of 2 is 0. Then minus sine of 0 is 0. Then minus, this minus is plus, cosine of 0 is 1. It's dv. So this is 4 times 2 is 8 times the integral from 0 to 1 of dv. This is 8v evaluated from 0 to 1, and all we have is just 8. Okay. Let me make mention of the orientation of surfaces. The orientation of a surface, we say that it's possible that a surface is said to be orientable, and that simply means that that there exists a normal vector n that is defined at every non-boundary point of S in such a way that the normal vectors vary continuously over the surface S. This surface is said to be an oriented surface. Now, what does all that means? It means here that a surface that is orientable has two surfaces. You restrict to calculate the surface integral only on one of those surfaces. If the surfaces overlap in a way that is convoluted, then we say that the surfaces here, that surface would be not orientable. In other words, up is always up and down is always down, or up is up and in is in. You can't have any hanky-panky where you thought this person was up and up and up, and then you discovered, oh, he's down. Okay, so hopefully that's not a bad illustration, but let's see if we can make sense of what we're saying. And I'll come back to the calculation in just a moment. Here is just a picture of a surface that is not orientable. If you take a pen and you draw on the outside and you go around, you will end up actually on the inside and not on the outside again. So this surface has a twist, and any kind of roller coaster twist, we said that the surface is not orientable. Okay, so let me go back now to seeing here that a surface z equal to little g of xy right here is defined as a surface. We want to be able to find a normal vector that's pointing outward. Well, it can point inward too, but outward is what we mostly use. So we define capital G. I've already defined this for you in the beginning of this section. So capital G is little z minus g of xy. From there, you recall that a unit vector is a vector divided by its own norm. So we're going to make n a unit vector. It is normal because we're dealing with this gradient of g, which is normal to the level curve. So here we have a unit normal vector, and this n is calculated in this fashion. It says here that n is pointing outward, and if we negate this gradient, n points inward. So here the gradient is negated, and so we have a downward or an inward unit normal vector. And then whether it's parametric surface or if it's just the surface defined in terms of x, y, and z, we calculate the gradient, and then from there we can simplify this norm into calculations of surface integrals and then later on fluid flow or the flux, and I'll show you that in just a moment. So here, this is the normal vector n that's pointing outward. You remember back in chapter 12 where you had to spend all that time trying to calculate the normal vector and the principal tangent vector, so much time with that. Here we have an easier way of getting those vectors here. So n is outward direction, so here S is oriented in an outward flow, and then if n is negative, then the orientation is inward or downward. Okay. Next we'll deal with the flux integral. Let me say that for just a moment.